All right, so going over this warm-up, I know there were some of you guys that were not here. That video has not been made yet. You guys are like a day and a half ahead of my second block. Just because you guys have had your flex already, they haven't had theirs. So not to worry, it will be up there. So for those of you guys who missed class last time, if you're still kind of lost at the end of this block, Monday it should be posted. Okay? I don't think it was a very terrible lesson. Was it pretty straightforward? I think most people liked it. Or at least most people didn't hate it. So we'll go that way. All right, so on number 1, and actually for 1 through 4, we're talking about continuousness. And this is kind of like when we were doing our domain restrictions. And it said, okay, is there anything that x cannot be? So in this case, is there anything that x cannot be? There you go, plus or minus the square root of 3. Because this is a rational. And for a rational function, that denominator cannot be equal to 0. So when we go through and solve this, wait a minute. When I go through and solve it, what's happening here? Yeah, we're going to have the square root of a negative. So is that going to give me a restriction? No. So since that is imaginary, and we're talking about continuity only over the real numbers, we get to actually just call this dude continuous. That's it. He is continuous. Okay? He is just straight up continuous. Does that make sense? Okay. For number 2, do we have restrictions on number 2? X cannot equal 2. Now, is that any of that going to factor away, cancel out? No. And if it doesn't cancel out or factor away, what does that leave me with? An infinite discontinuity. And where is that? At x equals 2. Bless you. Because we remember we had like 3 different discontinuities. We said things could be continuous. Things could have infinite discontinuities, which is what you have when you have asymptotes. Things could be removable discontinuities. Those are typically holes. Something like, hey, someone popped a hole in the wall. I can plaster over it and fix it real easily. Or I have jump discontinuities, which is not quite so easy to piece over. And those typically come from piecewise functions. What do I need to do with number 3? Factor. So how does the numerator factor? Beautiful. Watching those signs, it's always a bit of a doozy. And the denominator? Okay. And again, we're looking to see, okay, what's going to cancel out? Those are going to cancel out. But if I think about this, my restrictions would say that x could not be equal to what? 2 or 3. So that's my domain restrictions. Each one of those has to be some sort of a discontinuity. If it cancels out, what is it? It is a hole. So that means which one canceled out? The 2. So that means I'm going to have a hole at 2 for my x. And if I look at the simplified version, if I go and I put that 2 back in, but to the simplified one, what's 2 plus 3? 5. What's 2 minus 3? Negative 1. So that means my hole is at 2, negative 5. And what else do I have? And what do we call the asymptotes? Infinite. And where is that one going to be at? At x equals 3. Beautiful. We are going to have horizontal asymptotes. We're actually going to be talking about that today. But it's not going to affect our continuity. because the horizontal asymptote, an asymptote is strictly something that you're going to approach over time. You get closer and closer to it. You can bounce up and down above it. You can stay on one side or the other. But with horizontal, as long as you're still kind of like talking about not picking up your pen to draw it, and you can do that with a horizontal, it still can be continuous. Okay? Now this one is the one that I think trips up folks a lot. So does anybody know how to handle that? Yeah, because this is the main problem. What kind of a function is this? Sorry, well, yes, the whole thing is piecewise. What kind is that? Quadratic. Are quadratic functions continuous? Yeah, no matter what. Polynomials, period, are going to be continuous. What's that? Linear. Is that continuous? Yeah, so our only question comes when x equals -1. So if I plug -1 into the first equation, what do you get? What's -1 squared? -2. So I have the point here, -1, -1. And if I plug it into the second equation, 3 times -1, what is 3 times -1? -3 plus 2. So are those the same points? So what is that function? That guy is going to be continuous. Removable is another name for whole. No, your removable discontinuity, those are the guys that cancel out. Your infinite discontinuities are the ones that are left over. So we did have a removable discontinuity on number 3, because that stuff canceled out. But this x equals 3, like if I were, someone took all of my calculators, if I were to graph that, I would have seen an asymptote right there. Okay, yeah. No, I don't think so, at least. If piecewise functions, my main focus is if you check where the pieces change over, you want to see, are they the same point? And if they are, it's continuous. If they're not, they're discontinuous. I probably would not put a rational in a piecewise for this type of a problem. Okay? All right. And then when we're looking at end behavior, what is it that I need to find for each and every one of these? Highest exponent. So highest exponent is x to the 3rd. Highest exponent is x to the 6th. So we're looking at this and we're saying, okay, as x goes to infinity, as what does f of x do? And as x goes to negative infinity, what does f of x do? So I like to start thinking about the overall sign. This is negative, so how is it going to finish overall? Down. This number is even or odd? Odd, so how does it start? Same or opposite? Opposite. So that means as x goes to infinity, that's the right-hand side, what does f of x go to? Negative infinity. Good. And as x goes to negative infinity, which is the left, what does the f of x do? Go to infinity. So that's how I always approach it. I say, okay, it's negative, ends down, odd goes opposite. So for this one, is it going to finish going up or down? Finish going up. Is it going to start the same or the opposite? Same. Positive finishes going up. Even exponent starts going the same way. And I'm just trying to give you guys different ways that maybe you would be asked to do this, just so that you don't get too comfortable and just assume it's always going to go one direction. So, as x goes to infinity, what does f of x go to? Infinity as well. And for negative infinity? Infinity as well. Now, these guys are not polynomials. What are they? Absolute values. Which way is this absolute value going to open up? And this one? Because for these guys, it doesn't matter anything that's going on inside the parenthesis or inside the absolute value. It's all about what's on the outside. And again, I'm just trying to make it so you have to think a little bit and don't just go straight towards, like always following one pattern. So as x goes to negative infinity, what is f of x going to do? Go to infinity. As x goes to positive infinity, f of x goes to positive infinity. And on number 8, as x goes to infinity, or negative infinity, y goes to, and what will the other one be? I did that on purpose. And again, it's because I have no idea what order it's going to be on the test. And it really shouldn't matter what order it's going to be. You have to pay attention to look which one is it asking you for. So I would hate for you guys to have had a problem like this and then you weren't paying attention to what your signs were here and you flip-flopped them and got them both wrong. Okay? So I want you guys to kind of be aware and just pay attention to those little things. All right, let's take a look at your homework. I'm here if you've got questions. Yes, ma'am. Oh, 8 here. One more time.
The points were in the middle of 0 and 1.
Oh, so you're talking about for this one. Yeah, I don't care. If you said 0, 1.5, 1, that's fine. Sorry, I was just trying to figure out what you were looking at. Anybody else? Yes, sir?
How do you write removable and then write the coordinates as well?
Because the removable says that if I plug something in, if I define that point to be right there, if I take a little bit of a sticky stuff and I go stick it right there, there's no more hole there. Because if I plug that point in right there, I'm not going to have a hole anymore. Exactly. Where is that hole? We don't have, like when we're talking about an infinite, like these guys, thank you. When we talk about these guys, there's no place I can patch it because it's going to go towards infinity one way or the other. But a removable, if I were to just kind of take a little bit of spackle and fill that in right there, I would no longer have a discontinuity at that point. So that's why we call them removable. Okay? All right, ready for the other side? $210. Yes, sir. I hate it when you people say that. Yes, you are not stupid. You are in functions trig. You are not stupid.
I do stupid things all the time.
They're careless mistakes. You're just not being careful. Because that should be a 4. Thank you. So then when I plug a 2 in, that's 4 plus 4 plus 4, so that should be 12. Thank you. Okay. Any other questions?
So if it's the correct system and the piecewise, it's always a jump.
Usually it's going to be a jump. Yes. But if I, for example, you see how this problem I've labeled as continuous? If I said less than here and greater than here, that would have been removable because there's no, technically it would be the same point, but there is nothing at that point. Does that make sense? But yes, typically for piecewise, we typically have jump discontinuities. Yeah?
When you solve the piecewise and they don't match up, is it just the number of rows that it's equal to, or is it like?
Okay. So, today what we're doing is we are kind of looking a little bit closer at those rational functions. And for most of this, you guys have done this before. You did this in Algebra 2. We are adding one tiny little thing to it. But I try to make sure, because I know that this is a lot of writing, so I want you to just kind of highlight, fill stuff in here, because this is important, but I wanted to make sure you had step-by-step, no mistakes. How are you supposed to do this? So in order to graph a rational function, and rational functions are kind of crazy. You're going to have asymptotes, you're going to have holes, you have pieces going towards infinity, pieces not going towards infinity. It's going to look really weird sometimes. So the way that we do this, the first step is to always factor. You factor the numerator and the denominator. Factor, factor, factor. And if it factor cancels, that's going to be our whole. So you'll solve for x, and you would plug it in to the simplified, for the y. So you're going to look and say, okay, what of my factors cancel out? Figure out then what x would have been. Plug that back in and solve for your y. So that's kind of like what we did on one of our warm-up problems, if I can find it. That's what we did right here. We factored it out. We saw that these guys simplified. So I figured out what x was. I plugged it back into the simplified equation, and that's where my whole is. Now, if it doesn't factor out, if it doesn't cancel out, and it's left in the denominator, that's going to be your vertical asymptote. So if it cancels, it's a whole. That one's a removable. Discontinuity, and if it remains, it's a vertical asymptote, and that's our infinite discontinuity. So if it cancels, that means if I graph it, you'll have like a little open circle on your graph. If it remains, I'll have some sort of an asymptote on my graph. Then there's going to be one more thing that we need to check for. And this one's usually the place where people have the most difficulties, and that is going to be your horizontal asymptotes. And horizontal asymptotes are all about kind of understanding what your rules are. So for this first one, if the degree of the numerator is less than the degree of the denominator, what that could mean, that could be something like x squared plus 3 over, I don't know, x to the 4th minus 2x. If the degree of the top is less than the degree of the bottom, 2 is less than 4, right? You okay? So when that's the case, we're going to say our horizontal asymptote is going to be at y equals 0. Very, very important there. When the top is smaller than the bottom, you're going to have a horizontal asymptote at y equals 0. Now, if the top is equal to the degree of the bottom, so that would be something like, I don't know, 2x squared minus 5 over 3x squared minus 4x plus 2. I'm just making stuff up here. But what you need to see here, the degree of the top and the degree of the bottom are the exact same thing. Highest power on top, highest power on the bottom, exact same number. calculator away. This is all non-calculator. Nope. The degree of the top is equal to the degree of the bottom. Your horizontal asymptote is going to be coefficient of the top over coefficient of the bottom. So top less than the bottom, y equals 0. Top is equal to the bottom. All you're going to do is you're going to make a fraction out of those coefficients. Now, if the top is bigger than the bottom by 1, we have what's called a slant asymptote. It's not horizontal, it's a slant. And that's what I would get if I had, for example, x cubed plus 2x squared minus 4 over x squared plus 3. I don't know. Degree of the top is exactly 1 more than the degree of the bottom. Okay? Yes?
So for that, you're looking at the biggest one.
On all of these, you're always looking at the highest power on x. That's why I try to mix up. Some have extra x's, some don't. But you're always looking for, see, the highest power here is 3, highest power here is 2. If the top is 1 more than the bottom, we have a slant asymptote, and we're going to need to divide that out. And so literally what you're going to do is you're going to say x squared plus 3, and you divide it into x cubed plus 2x squared minus 4. And it sounds a lot worse than it is. Don't worry, it really is not that bad. We're not going to do that right now. Okay, but we'll get to examples like that. Please, please, please do not freak out. Okay? Yeah. If it is more than 1 greater, like the top is, I don't know, x squared, the bottom is 2, you are not going to have a horizontal or a slant asymptote. Okay? So the steps that we do here, again, very important. You start factoring the numerator and the denominator. You're going to look, does stuff cancel out, yes or no? If it cancels out, it's going to be a hole. If it's still in the denominator, it's going to be a vertical asymptote. Then we think about our horizontal asymptotes or slant asymptotes. If the top is less than the bottom, boom, just say y equals 0. That's your asymptote. If the top and bottom are equal, you take those coefficients. That's your asymptote. If the top is 1 more, that's going to be the kind of the annoying one. You got to take a step further and divide. If it's more than 1, you don't have one. Okay? So let's try some problems. And again, we're going to do this without our calculators. Put the calculator away. There you go. He's like, but I like it, Chase. Put it away. I don't even want you to try to reach for it. All right, ready for this? What is my first step? Factor. Does the top factor? Yeah, what does it factor to? X plus 4, x plus 2. Does the denominator factor? Yes. How does it factor? Okay. So now we're going to go through our different characteristics. Holes. Do I have a hole? Why don't I have a hole? Yeah, nothing cancels out, so we don't have a hole. Then I think about my vertical asymptote. Do I have a vertical asymptote? Yeah. Where are my vertical asymptotes? 0 and... So how do I write my vertical asymptotes? X equals 0. X equals negative 3. And I want to see those written out separately because those are equations of lines. And I'm going to go over to my graph. And when x is equal to 0, I'm going to draw an asymptote. Asymptotes are always dashed lines because they're guidelines for us. And then I have x equals negative 3. So I'm going to draw another dashed line right there. Okay. So we've done holes, we've done vertical asymptotes. Now let's think about horizontal asymptotes. What is the degree of the top? 2. What is the degree of the bottom? What is true about those two numbers? They're equal. So when they're equal, how do we find the horizontal asymptote? Yeah, you just look at the coefficients. So y is going to be equal to, what's the coefficient here? 1 over 1. And what is 1 over 1? 1. So I'm going to have a horizontal asymptote at y equals 1. You are only ever going to have a maximum of 1 horizontal asymptote. You can have a whole bunch of verticals. You can only have 1 horizontal. Okay? Now, this is really important, what we've just done. We've figured out our main guidelines. So what we need to do is we need to plot 3 or more points on each side of the vertical asymptote. So what that means is I want to get a couple points here, a couple points here if you can't get 3 because there are only 2 spots in there, okay, and a couple points here. And then we want to find x and y intercepts as 2 of those points. So how do I find an x-intercept? What do you do to find an x-intercept? Yeah, because what are you doing? X-intercept, you put something in for something. Y is 0. X-intercept, you're going to put y equals 0. And really, you can just deal with the numerator. Okay? So when I solve that, what am I going to get for x? -4, -2. So when y is 0, I get -4 and -2 as my points. I'm going to go to my graph here. So 1, 2, 3, 4. There's 1 point. 1, 2. There's a point. I need to find my y-intercept. How do I find my y-intercept? Plug a 0 in for x. So when I plug a 0 in for x, I'm going to have 0 squared plus 6 times 0 plus 8 over 0 squared plus 3 times 0. What's this denominator going to be? 0. And when something is over 0, you're undefined. So I just tried to find my x-intercept by plugging 0 in, my y-intercept by plugging 0 in for x. And you have no possible point because look at what happens when x is 0. What do we have? An asymptote.
Wait, so why did you plug it into the original function and not the simplified?
It doesn't matter really which one you plug it in. A lot of times I'll be plugging it into the simplified version, but if you remember, nothing's simplified here. And when you're plugging values back in, sometimes I think it's easier to go into the original. Yes, ma'am?
Why can't you only use the numerator to find x?
When you're finding the x-intercept, because if y is 0, and I'm trying to solve this, my first step would have been to multiply both sides by x squared plus 3x. And that times 0 is going to give you 0 anyway. So good question. So I have 2 points on my graph, and I want a couple points more. I start by finding the x-intercept and the y-intercept if we have them. Then what we're going to do is we're just going to randomly pick points. So I want to find what my point is when x is -1, 0 doesn't work, 1, 2, 3, and let's go 2 more over here. So that's 1, 2, 3, 4, 5, 6. Okay, and all I'm going to do is plug it in. I do not care if you plug it into the original or the factored form. Really, I don't. Give you the same thing. When I plug -1 in, like for example, if I plug it in here, what's -1 plus 4? 3. Negative 1 plus 2? 1. So 3 times 1 is 3. When I plug negative 1 in here, so that's going to be negative 1. Negative 1 plus 3? 2. So that's going to be negative 2. All I'm doing is plugging the numbers in and see what I get. So at negative 1, I'm at negative 3 halves. So I'm right here. Those are the only points I'm going to have inside this guy. So I'm going to draw that. When I plug in 1, 1's an easy number to plug into this stuff, so I'm going to do it here. What's 1 squared? One more time. 1. 6 times 1? So 1 plus 6 plus 8? 15. 1 squared? One more time. 1 plus 3 times 1? So that's going to give me... So 4 goes into 15 about how many times? Almost 4. So 1, 2, 3, almost 4. So what I want you guys to do is I want you to finish these coordinates so that we can have more points to plot. Okay, you guys got those? Okay. Ready to see my graph? So the graph that I got looks like that. And what's really nice, that's what it should have been. Does that match okay? And these were the points that you should have used. All right? By the way, if you find yourself at home without a graphing calculator, desmos.com. Okay? All right, let's do another one. What's my first step? Factor. So the x minus 3 is not going to factor. How does the denominator factor if it does? X, one more time. Plus 5 and minus 3. Beautiful. So what's going to happen with this? Cancels out. And when it cancels out, what does that become? A whole. So I'm going to have a whole when x is 3. And so I can actually simplify this now and use a much easier equation. So I can use that for everything else. So when I plug 3 in here, what is 3 plus 5? 8. So I have a whole at 3, 1, 2, 3, and 1/8. So just above that line, I've got a whole. What else do I have? A vertical asymptote. Where's my vertical asymptote going to be? X equals, one more time, negative 5. 1, 2, 3, 4, 5. So that's where I'm going to be. And you're going to see it makes a whole lot less work when we have just one asymptote in here. This is going to have a lot fewer points. All right, I can look at my simplified version. What else do I need to figure out? Is there a horizontal asymptote? Where is my horizontal asymptote? Why is it 0? Because 1 is less than 2. When the top is less than the bottom, your horizontal asymptote is automatically going to be at y equals 0. But you're not going to see that line when I draw on the map. Yes, sir.
If the horizontal asymptote is 0, how is there an x that just x equals 3?
There isn't an x-intercept at this. Oh, this is my hole. This is my hole at 3, 1, 8. Okay? All right, so let's go for my x-intercept. How am I going to find an x-intercept? What do I do? Put 0 in for y. And when I put 0 in for y, I'm going to have 0 is 1 over x plus 5. What do I get with that? Well, it's not going to happen. It's not going to happen because you have an asymptote right there. Okay? And then I want to find my, let's do y-intercept next. How do I find a y-intercept? Plug a 0 in for x. So I'm going to have y equals 1 over 0 plus 5. So what's my y-intercept? 1/5. So when x is 0, y is 1/5. So it's just about right there. So I have no x-intercept. I found my y-intercept. Now all I need is a couple of points on either side of this. So I just need one more point on the right because I've already got 2. So I'm going to go 1, 2, 3, 4. Right? 1, 2, 3, 4. So I'm going to use negative 4. I'm going to do 4, 5, negative 6, negative 7. And that should be good enough because I'm kind of off the graph beyond that. You can do a negative 8 if you want, but 1, 2, 3, 4, 5, 6, 7, 8. And what I really like to do with this stuff, watch it how much easier it is to plug these guys into the simplified formula. I'm going to have 1 over, what is negative 4 plus 5? 1. So at negative 4, I'm going to be at 1. So this graph is going to come right like that. When I plug negative 6 in, I'm going to have 1 over, what is negative 6 plus 5? Negative 1. Oh, that's easy. It's going to be right there. When I plug negative 7 in, I'm going to have 1 over negative 2. So 7 1/2, negative 1/2. And because it's easy, when I plug 8 in, what am I going to have? Negative 3. Are you guys on the same page with me? Just irritated that I'm making you do that without a calculator? A little bit. No. BT dubs in the race between coffee and Benadryl. Coffee is starting to edge out Benadryl. Just giving you a heads up.
So when we graph it, do we have to make the whole more obvious? It's like on your, or is that fine?
That's fine. That's fine. I do need to be able to tell that you've got something there. But I get it. When you draw through it, it sometimes looks like it colors in. So just try to leave an open circle or make it big enough to see that it's an open circle. All right. Start me off on this. I want you guys to do what first? Factor it. I want you to factor it. I want you to find any holes or asymptotes. Check your neighbors on what you got for your holes and your vertical asymptote. This is what? I knew it. Yes, I can. Just watch. Okay. Ready? Yay! Okay. All right, so no hole, no asymptote. No hole, no asymptote. Is it continuous? Yes, this guy is going to be continuous. Okay? So what we do need to find is we still need to find the intercepts and a couple more point steps to make sure that we know what this weird graph is going to look like. And it is a weird graph. So, oh, yep, sorry. Forgot about that one. So I'm going to have a horizontal asymptote where? One more time. Thank you. Y equals 2/3. Did everybody catch that? Do not give me 4/6. If it is a fraction, you have to simplify. So y equals 2/3. And you know what I'm going to do? I'm actually going to bump this up to make it a little bit easier to graph here. I'm going to call that 1, 2. Okay, so I'm zooming in on my graph a little bit to make this a little easier because this is going to be a weird looking graph. So when I plug, let's see here, 2/3 is going to be right here. And then I just set my scale to make my asymptote easy to draw. That's really my whole point behind that. Get it? Graphing points? No? Yeah, kind of sad. All right, so what do I need to find first, point-wise? Yeah, because I was like, I am not going to graph 2/3. That's going to be way too tiny. What else do I need to find? I've got my pole, vertical asymptote, pole, horizontal asymptote. X-intercept. How do I find an x-intercept? Set y equals 0. So I'm going to have 0 equals 4x squared minus x. Because if I multiply both sides by that 6x squared plus 5, that's times 0. It just goes away. What makes this 0? 0. Because you can think about that in factored form. X times 4x minus 1. So that's going to be at 0. And it's also going to be at 1/4. Okay, so x is 0. It's going to be 0. Hang on. What do you mean 4 times 0 is 0? Oh, no, this here should be positive 1/4. Because if I solve this, I would add 1 and divide by 4. Oh, that is correct. So I would be over 1/4. I'm right about here. Okay? All right, well, the great thing here is the next point I would have needed to find was my x-intercept. I'm sorry, y-intercept, which I also have already because it's 0, 0. So I'm just going to find a couple of points. Let's see what happens when I plug in -1 and +1. So -1 squared is times 4 minus a -1. -1 squared times 6 plus 5. Okay, so I'm going to go over -1, and I'm going to go up. That's a little bit over 1/2. Up, sorry. Remember, you changed the scale, Augsburger. What do you mean? Oh, yeah, it's about. Yeah, you're right. Okay. I was like, what are you talking about? My bad. All right, when I plug 1 in, 4 times 1 squared? 1 times 4 minus 1. 1 squared times 6 plus 5. So over 1, about here. And what's going to happen with this graph? He's really weird looking. And just kind of show it to you. That's what that graph looks like. And I can keep zooming in. So this was about the scale that I had on mine. So it goes just a little itty bitty bit under. But there you go. Isn't it beautiful? That's a really weird looking graph. Little divot. All right. And just so you guys know, we have 3 more problems. And then I'll give you your homework. Okay. What do you do on that first problem there? Do it. I'm going to make you factor it. Factor it all.
That's the second problem. Guess what?
Oh, I got the wrong problem showing. Sorry, my bad. My bad. Shut up. Don't make fun of me.
Yes, I do. -3, -1. No, it doesn't have to be. That's not true. Oh.
So what are we fighting about?
I don't know about it factored.
Whether or not it factored. Does it factor? No, it doesn't factor.
I was just kidding, you guys. I was trying to test you.
That guy doesn't factor. Yay us.
I'm getting fired.
Okay? So that does not factor. So what does this mean? What do I have? I have an asymptote. What kind? I have a vertical asymptote. Where is that guy? X equals -2. If you leave off that x equals, it's no longer a line, so it does make a big difference. All right, what's the degree of the top? What's the degree of the bottom? Uh-oh. What do I have? A slant asymptote. Do not freak out. She's gonna freak out. So we are going to have here a slant asymptote. Now, you have a couple of different ways that you could do this. I don't care which way you do it. You can do long division or you can do synthetic division. Long division is actually not that bad. I think long division with polynomials is easier than long division with numbers. That was last year. So what we're going to do, this is the denominator. So that goes out front. Then I'm going to have x squared plus 4x minus 3. And this is so nice. I love looking at dividing polynomials because all I need to look at is the first number. That's it. The first number. So x times what gives me x squared? X. So I'm going to put the x above my other x. Line it up. X times x is x squared. X times 2 is? And then what we do here is we subtract those. What's x squared minus x squared? 0. What's 4x minus 2x? And drop down the 3. Okay? So x times what gives me 2x? 2. So I'm going to line it up with the other integer. 2 times x? 2 times 2? But what I'm doing here is subtraction. So what do I have? 0, -7. Do I have anything else left to drop down? This is my horizontal asymptote. You don't need to go any further. I promise. Because basically, it'll come back to you. So how do I graph that line? Where do I start? I start 2 on the y, and then I go up 1 over 1, down 1 over 1. So this is going to be my slant asymptote. By the way, this was long division. I am actually a bigger fan of what's called synthetic division. Synthetic division, if you recall, if you don't, that's okay. I'm just going to give you a quick little refresher course. You're going to take the coefficients. Coefficient of x squared, of x, of my constant. What would my 0 here be? -2. And what you do here is pretty straight. I'll do one of these for each problem that we're going to do division, so you can choose for yourself if you'd rather do long or synthetic. Drop it. Times. Okay? Add. 2. Multiply. Add. So this is my constant. That's my x. That's my slant asymptote. I will do this for each of them, and if you need more practice on long and synthetic division, I can show you some of those because, like I said, we don't have too many problems left. I don't care whether you use this or this. Whatever makes the most sense to you. I get synthetic division is a trick, and tricks sometimes are very easy to forget. Obviously, it takes a lot less time, but if you don't remember the rules, you're not going to be able to get to that.
So it's just you multiply.
You drop, multiply, add, add. Okay? All right. So what else I need to do here? I found my only asymptotes, so I had a slant asymptote at y equals x plus 2. I have a vertical asymptote at x equals -2. What else do I need to find? X and y intercept. Now, the easiest one I think to find is actually the y-intercept. What do we do for a y-intercept? Plug in 0 for x. And the reason why I think that is so easy is watch. 0, 0, 0. So what is your y-intercept? -3/2. So I'm going to go to 0, 0, -3/2. Okay? Now, to find the y-intercept, how do I find the an x-intercept? Sorry. Put in 4y. This guy's going to be a little bit trickier because I'm going to set this here equal to 0. When I cross multiply, that x plus 2 goes away, and I'm left with 0 equals x squared plus 4x minus 3. But we've already said that does not factor. How do we solve a quadratic that does not factor? You could complete the square if you wanted to. It'll give you the same answer as the quadratic formula. So x is equal to, our quadratic formula is what? -b
Plus or minus square root of 2.
b squared
Plus
minus 4ac.
all over 2a.
Okay, guys? You need to understand, if you remember anything from algebra, you need to have the quadratic formula memorized, especially if you are going on to any other class after this. They fully expect you to memorize the quadratic formula. Okay? So I'm just going to figure out what this gives me. X equals, what is b? 4. So negative b is -4 plus or minus the square root of, what's 4 squared? 16 minus 4 times a times c all over 2a. So what's a negative times a negative? Positive. 4 times 1 times 3? 12. So 16 plus 12. 28. Does the square root of 28 simplify? What perfect square? 4. 4 goes into 28 how many times? 7. So this is 2 square roots of 7. So when I simplify that, I'm going to have negative 2 plus 2 root 7 and negative 2 minus 2 root 7. I'm sorry, minus the root of 7. Because the 2 is gone. Because I divided by 2. And I really don't want to draw that. And then it's easy if you just kind of pick some other points. So I'm going to go with a point here. I'm going to go with negative 1. When I plug negative 1 in, what is negative 1 squared? 1. Plus 4 times negative 1. So 4 times negative 1 is? Negative 4 plus 1? Negative 3 minus 3? So I'm plugging negative 1 plus 2? 1. So at negative 1, I'm at negative 6. 1, 2, 3, 4, 5, 6. I already have 0 plugged in. Let's plug in a positive 1. What is 1 squared? 4 times 1. So 1 plus 4 minus 3. 1 plus 2. So I'm going to be at 2/3. So my graph is going to look like that on the right. Ladies and gentlemen, please focus. And on the left, I'm running out of room to kind of do stuff here. So on the left, let's see here, that's 1, 2, I'm going to plug in negative 3. And if you need to write it out, write it out. So this is going to be negative 3 squared plus 4 times negative 3 minus 3 over negative 3 plus 2. So what is negative 3 squared? 9. 4 times negative 3? So 9 minus 12? Negative 3 minus 3? Okay. Negative 3 plus 2? So negative 6 over negative 1? So 6. So I'm going to go to negative 3. 1, 2, 3. 1, 2, 3, 4, 5, 6. I'm going to use negative 4. What is negative 4 squared? What is 4 times negative 4? Negative 4 plus 2? So I have negative 4 over negative 2, which is 2.
Why is it minus 4 now?
You mean why am I using a negative 4 here?
Up there at the end.
Oh, did I write the wrong number down? Sorry, thank you. Silly Miss Augsburger. Get that down a bit. And let's do negative 5. And this is the most irritating part of the whole thing. Hopefully you notice that. Negative 5 squared. 25. 4 times negative 5. Negative 5 plus 2. So 25 minus 20 minus 3. So at 5, 1, 2, 3, 4, 5, I'm going to be at negative 2/3. There's my graph. Kind of a weird looking dude, isn't he? So what I'm hoping you guys see with this is that the stuff that we're talking about today, the asymptotes, the holes, that should be the easy part. The hard part is figuring out the stupid points. And you get that just by plugging it in and doing arithmetic. And to me, that's the hardest part. So, it would be easier if you could use calculators. No, it's because when you go to calculus, these guys have very specific implications, so they do not want you doing it with calculators.
Why?
Because you won't be able to do the calculus aspect of it with a calculator. At least not in a sense that, I mean, yeah, you could probably get your calculator to do that for you, but you wouldn't get credit for it.
Well, that's stupid. We have calculators for a reason.
All right, so I want you guys, this one's not nearly as bad. This one is much nicer. Because this one factors. Yay! Factor it. Come on, ladies and gents. I want you to factor it and find vertical, asymptotes, holes, whatever. We'll talk about putting points in when you're done with that.
So when you do this synthetic division, what number do you put outside? The opposite of the number?
It's a 0, yeah.
It's a 0. Oh, the 0.
The 0 for the denominator. Yeah, sorry. This one is one of those that it's almost so easy it's difficult when you actually start to graph it. Because people also oftentimes second guess themselves on a problem like this one. So, did you have any holes or vertical asymptotes? You have a hole. Where is the hole? -1, -1. Do you have any vertical asymptotes? Do you have any horizontal asymptotes? Do you have a slant asymptote? We do have a slant asymptote. The degree of the top is exactly 1 more than the degree of the bottom. Yep, but if we look at it, if I were to divide it through, I just get 2x plus 1. So that is a slant, and it's your simplified equation. Huh? Well, you could do points. We do the points if I can't tell by looking at the equation how to graph it. I mean, like, you could put points in here, and you would have come up with your y-intercept would have been 0, 1, x-intercept would have been 0, 1, -1/2. You could have put in 1, 3, 2, 5. On the other side, -2, -3. So all of those are points also. Oh, wait. Yeah, go ahead. Oh, wait. Oh, wait, oh, wait, oh, wait. All right, so we are really kind of running out of time here, so we won't get to this last one. We'll save that for next class. I'm going to give you guys your homework. Your homework is a worksheet.